Let's do together. Okay, we have done example 3. All right. Let's do example 6. Okay, in this example, the uniform 5-meter long round wooden rod is tied to the bottom by a string. Determine tension in the string. So, the first question asks the tension. Where is the tension? Tension normally happen at the string. So, this is the tension. The tension shall be downward. This is tension. Alright. And then we have two forces, okay, which is the weight of the rod. So the weight of the rod basically at the center of the geometry. Okay, so this is 5 meter long. Definitely it is half of it. So it is 2.5. So this is the weight of the rod. And then we have another force, which is buoyancy force that will cause this rod floating. All right. So where is the buoyancy force, class? Where is the location? Anyone knows where is the location of buoyancy force? FB?
In middle of submerged area.
Yes, perfect. Where is the submerged? Is it 5 meter or 4 meter submerged?
4 meter.
4 meter. 4 meter divided by 2 is 2. 2 meter. So, the buoyancy force acting for the submerged body from here to here. Okay. So, it should be down here. Upward. And this is FB. Okay. So, how to calculate the tension, which is the T here? We can use the summation of force in Y direction. Okay. So, summation of force in Y direction is equal to 0 because this is equilibrium, static. So, what's the force involved? We have FB, positive upward. We have FB plus, and then we have minus W. And then we have minus tension equal to 0. To calculate the tension is equal to FB minus W. Alright. So, this is how to calculate the tension. Okay, let's check. Okay. FB upward positive minus W minus T equal to 0. Alright. So we move. Okay. So, how to calculate the FB? Any idea? Remember, it's very easy. In order to get FB, okay, we can use the equation. Okay. Rho G V. V is a displaced volume. So, rho is the rho of water. We can use 1000 And the gravity 9.81. And then the displaced volume. How to calculate the volume of displaced? What's the shape of this rod? Anyone knows? The shape is
Round. Bulat.
bulat, round. Okay, that is the cross-sectional. How about the volume? What is the formula for this geometry? It is cylinder, right? It is cylinder. So we can calculate the volume of the cylinder, which is pi r squared h. Okay, area multiply with distance. Okay. Okay. So pi multiply with radius, which is 0.08 meter divided by 2 squared multiply with the height, which is 4 meter. Okay. So what did you get? You will get 196.84 Newton. Alright. The next part, you know the FB, you can substitute the FB. How about the weight? The weight of the road. Any idea how to get the weight of the road? So in order to get the weight of the road, okay, is it possible if we can use like this? Weight equal to mass multiply with gravity, mass of the road. Mass is equal to mass gravity K rho G V. Do we have the density of the road? No. We have only the volume of the road and the gravity. The density of the road is not provided. Okay, it is not there. So do you think we can use this equation? Definitely cannot. So what can we do now? We can use the summation of moment at point T. Okay, if we do the summation of moment at point T, anti-clockwise, positive equal to 0. When we do at T, we can eliminate T. Alright, so to ease the calculation, we do the summation of force, summation of moment. Okay, anti-clockwise. Okay, moment at T equal to 0. So, in order to have the summation of moment, the force, we know that the moment is equal to force multiplied with radius. The force must be perpendicular, alright, to the radius. It must be, okay. So, this road shall be have the perpendicular force. So, this W, we need to divide into X and Y component. Let's say this is, okay, this is WX. Alright. And then the FB as well. This is FBX. Okay. Alright. So, okay, let's say this is FB. FBX. So we start from the T here, okay, going to WX and then follow WX, which is anti-clockwise. So WX multiply with 2.5. This is positive, yeah. Okay, because from T we go to W and we follow the WX. So it is, you use your right hands. Okay, you right hand rule. Okay, you try to rotate, it will be counterclockwise. So it is positive. Alright. So and then you follow for the FBX. Okay, from this one, from T go to FBX. So it is clockwise. It is negative. Negative FBX. The distance is 2 meter. Equal to 0. We know that in order to get WX, okay, we have the theta here. This is theta, okay. This theta is basically equal to this theta. This theta also equal to this theta. In order to get WX, okay, WX is equal to W cos theta. For the FBX is equal to FB cos theta as well. So substitute to this equation, W cos theta 2.5 minus FB cos theta 2 equal to 0. Then cancel out cos and cos. You will have the W equal to 2 over 2.5. Okay, FB. Okay, so we can get the W, which is 2 over 2.5 multiply with FB, this one, 196.84 Newton. So 196.84 multiply with 2 divide with 2.5, which is 157.47 Newton. Alright, so to calculate the T, substitute again. T equal to FB 196.84 minus 157.47. You will get the final answer to be 39.38 Newton. Okay, that is the tension. The next question, specific gravity of the wood. So the specific gravity is Sg. How to calculate the Sg, which is the gamma of the wood divided with the gamma of water. Okay, this water lah basically. So how to calculate the gamma of wood? Okay, you can see here. Alright, this is the weight. The weight of the wood or the root. Okay, to simplify the equation, we can use this one. This is for A. This is for B. So the weight of the root is equal to gamma of the root multiply with volume. Alright. So in order to get the gamma of the root, the weight of the root divided with the volume. So the weight of the root is here, which is 157.47 Newton, divided with the volume of the root. Okay, what is the volume of the root? Okay, the volume of the root is pi r squared h. So 0.08 over 2 squared multiply with the total length, which is 5 meter. Okay, you will get here, divide with pi, 0.04 squared, 5. Okay, you will get 6265. Okay, 6265.61. Okay, so from here, substitute to the equation, specific gravity of the root. Okay, of the wood, the same lah, the wood, the root, okay, is equal to the gamma of the wood, which is the same here lah. Okay, over with gamma of water. Alright, 6265.61 divide with gamma of water, which is 9810. Okay, you will get 0.64. Okay, that is the final answer. Okay, is there any question? Okay, class, do you understand?
Yes, doctor.
Okay, thank you. Now we proceed to the next part, which is the stability of submerged body. So when the body is submerged, for example, the body in this kind of shape. Okay, this is water. Do you think the object will stable? So how to check whether this arbitrary shape of body is stable or unstable in the water? So we must know the center of gravity and the centroid. So from here, let's say the center of gravity is here. Okay, this is G. And then the centroid is here. So the force, basically the weight of the body will act at the G. And the buoyancy force, remember, will act at the centroid. When you have a small disturbance in this direction, this object will rotate. So it is unstable because it is meeting each other. The FB meeting the, okay, the W meeting the FB. Okay, it will have the rotation. It will not stable. For the case of neutral, you have the arbitrary shape. Okay, and then the center of gravity and the centroid is at the same point. Okay, so the buoyancy force acting at the centroid is equal to at the same position as the weight of the object. So this one is meeting to each other. This is neutral. Okay, it will not move at all. Okay, for this unstable, you give a small little disturbance, it will definitely rotate. For the stable case, we have the arbitrary shape again. Okay, and then we have the center of gravity at the bottom. And then we have the centroid. So you look at here, the buoyancy force is away from the wick. This is the wick. So what do you think when one person try to pull to the knots and another person try to pull to the socks? Do you think the object stable when you give a disturbance, little disturbance? You think it will rotate or remain to the original position? Class, what do you think? When we have one person pulling to opposite direction, do you think this is stable? Definitely stable. Okay. Even logically, you try to push one thing to the opposite direction and suddenly another friend try to disturb at the center, it will remain the same position. It is always stable. Okay. The means it is stable is you try to give a small disturbance, it will remain to the original position. So same thing like this. This is stable. Okay. You try to give the disturbance motion at the right side, it will remain to the original position. For the neutral, you give a disturbance and it will stop here. Okay. For the unstable, you give a disturbance, it will move continuously. So how to know the object stability? Okay. So to make sure you understand well, okay, let me draw to you what is C and what is G. For example, we have this kind of things, okay. We have this shape. Okay, what do you think the center of gravity, the G? Where is the location of G? Class?
Center.
At the center. Perfect. Thank you, Daus. Okay, at the center. This is G. Where do you think the centroid? The C.
At the same place.
Okay, why at the same place?
Bentuk dia sama, geometric kan.
Okay. You must know before you assume it is at the center if the body is completely submerged in the water. So you try to take out the displaced one. This is the displace of the liquid. Okay, the same shape, right? So definitely the displaced, this is a displaced volume. Okay, so definitely the centroid is the same. Okay, so the buoyancy force acting in the same direction to the wake, to the same point. However, if I try to, okay, if the body is half floating, half submerged, what do you think of the centroid?
Below
Below?
gravity.
Yes, below center of gravity. Now, the displaced volume is this one. This is a displaced. So remember the centroid must refer to the displaced volume. Where is the displaced volume? This one. So definitely we must refer only this one. So where do you think the centroid acting at the blue color? Maybe like in here, right? So this is centroid. So now can you see the difference? How to differentiate between C and G? So definitely the C will be the buoyancy force, and the weight at the centroid. Do you think this is stable? When someone try to push each other, do you think this is stable or not?
Yes.
Okay, why it is stable? Okay, this is stable or not stable? Unstable.
Unstable.
Unstable. Unstable. You can see the direction. Okay. You give a small disturbance, it will rotate. You can see as here. It is unstable. Okay, now you know, yeah, where is the C and where is the G, how to determine and C and G. Okay, the G always the same, even it is at different place. Okay, it is at the air or in any space, the G always the same. It refers to the geometry. The C is different. It refers to the displaced volume. Okay. For sure, if you understand the concept of stability, it will be easier for you to understand the object stability. Okay, we have the boat. Okay, and this boat is before rotation. This is after rotation. That means maybe due to the wave, okay, heavy wave, it will rotate. This is after rotation. Okay, this is before. That means it is at initial stage. So when you give, when there is a wave, it will rotate automatically. So do you think this boat stable because of the wave? Okay, disturbance. So you must check the metacentric height, GM. GM is the distance from G to the point of intersection, buoyancy before rotation and after rotation. Very simple. Okay, this is G. The axis is here. We must clearly specify the axis. Okay, this is axis. So the gravity, the center of gravity is always the same. At G here, nothing changed here for the G. Alright. So this is for C. C is a centroid. The centroid will refer to the FB, the buoyancy force acting vertically upwards, and the G acting downward, the weight. Okay, we have the weight here. So after the rotation, what happened is the axis still the same. Okay, but the difference here is the C, the location of C. Why the C change, class? Any idea why the C change?
Uh, the volume of the submerged ship is different.
Yes, different. Initially, the volume of displaced ship is this one. Due to the rotation, now what happened to the volume of displaced? So, displaced volume changing. Changing of the displaced volume will change the centroid. So, the new location of centroid is here. So, this is the buoyancy force acting here. The weight here. Okay. So, this line, okay, straight to this line is the point of intersection. So, the distance from G to M is the metacentric height. We call as a GM. Okay. So, the GM, to know the stable or unstable, if the GM is positive, okay, That means it is stable. If Gm is negative, it is unstable. For example, like this. This is M, this is G. Okay. So, the M is on top of G, right? So, it is positive. When it is below the G, it is negative. It is unstable. This is stable. So, the G, where is the wake? The wake acting at the G. Okay, this is the wake. For the M, the mass, the intersection, this is buoyancy force. Okay, do you think this is stable?
Yes.
Yes.
Yes, it is pulling each other, right? It is pulling each other. So you can see the M on top of G. It is stable. What happened? Okay. What happened? This is G. And this is M. Of course, this is unstable lah. Let's draw the force. Okay, this is the wake. And this is the buoyancy force. Can you see? Is this considered stable? No, this is unstable. Okay, when we have the arbitrary shape, it will definitely rotate. Clear? Okay, class, are you understand the concept now?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Okay, good. So to calculate the GM, whether it is positive, where you must refer to M. M must be on top of G. This is the very simple formula. GM is equal to second moment of inertia, the displaced volume minus CG. Okay. So let's take a look at the example. We have a 0.25 meter cylinder is 0.25 meter long and composed of material with specific gravity. So, specific weight. Specific weight is gamma, ya. Gamma of the material. Let's say gamma of M, which is 8,000 Newton per meter cubic. Will it float in water with the end horizontal? Okay, so that means this is floating cylinder. Let's draw the floating cylinder. Okay, this is on top view. Okay, from the side view, yeah. Okay, so definitely we can see lah from the top view, it is a cylinder. Okay, the diameter basically 0.25 meter. And it is 0.25 meter long. Okay, from here to here is 0.25 meter. Okay, so let's say this is submerged in, it is floating because will it float? Okay, that means we have to specify this is floating case. All right. So from here, we must understand how to differentiate C and G. Okay, class, where is the position of G? Where is G?
At the center of the
At,
shape.
yeah, so what's the value?
by
Yes, it is at the center. So what's the value of G? The location of G. Okay, yes, it is perfect. This is G, right? Okay, so where is the value? Definitely 0.25 divide with 2. Okay, clear. So from here to here is half of the total length. So 0. Okay, 0.125. Betul ke? Can you check? Okay, 0.25 divided with.
betul.
Okay, okay. 0.125. Okay. So, where do you think the location of centroid? The C. The centroid.
Below G,
Below G. Why below G?
dia float.
Okay,
Uh,
the C must refer to the displaced volume. So this is displaced volume. Right. So this is C. Alright. So how to calculate the C? Do you know how to get the C? The location of C? Any idea how to get C? This C, very simple. This C from here lah basically. Any idea how to calculate C? First we must know what data we must get to get C. We must know total what? The total of what we can get C. Remember C depends on what?
Displaced water.
Okay, displaced water. So we must know the total depth, right? If we know the total depth, okay, let's say this is depth. We can divide with 2. So we can get C. So how to calculate the depth? So this is the question. Alright. In order to get the total depth, alright, we can use the buoyancy force. So this is under the equilibrium state. So where is the location of buoyancy force? The buoyancy force must be act at the bottom. Okay, this is FB and this is the weight. Alright. So based on this, we can do the summation of force in y direction equal to 0. So the buoyancy force or the weight is equal to FB. Okay. So let's see. The FB equal to weight, the same thing lah. So FB is rho G V. V displaced equal to the weight of the cylinder, which is, it is given gamma multiply with the volume. Okay. Rho G we can simplify into gamma as well. Okay, I want to change into gamma lah, gamma of water. Okay, so in order to get the displaced volume, okay, gamma of material multiply with the volume of the whole body divided with gamma of water. So gamma of material given with 8,000 multiply with the volume. So what is the volume of this cylinder? Which is pi. Okay, pi over 4, 0.25 squared. Okay, multiply with the height, the total height, which is 0.25. Okay, divide with the gamma of water 9810. You will get it is 0.01 meter cubic. That means the displaced volume here, okay, is 0.01 meter cubic. So how to calculate the depth? Okay, it's very simple to get the depth. Okay, the depth is basically displaced volume divided with the area. Okay, this is simple. Okay, this is area and this is the depth. And this is the volume. So volume equal to area multiply with the depth. To get the depth is displaced volume over area, right? So just substitute displaced volume D here is 0.01 over area. So area again is pi over 4 multiply with 0.25 squared. You will get 0.204 meter. So now you can get the C. C is 0.204 divided by 2, which is 0.102. So this is C 0.102. Okay. So after we have discovered all the parameter, let's use our equation. Okay, the equation to get the metacentric height, which is Gm. Okay, our equation Gm is equal to second moment of inertia I naught over with displaced volume minus Cg. Okay, you can see that we can have I naught using the equation. Okay, we can have the displaced volume we have already, the Cg we have already. Okay, so now we can calculate the I naught. I naught. So I naught is second moment of inertia. You can look at the table later on. Okay, to know the geometry of second moment of inertia, different geometry will have different moment I naught. When it is rectangular, it is BH cube over 12. When it is circular, it is pi d the power of 4 over 64. So it is different. So how to know the geometry? You must look at here. Will it float with the end horizontal? That means when we look at the geometry from this view with the end horizontal. So this is end. Will it topple down or will it not topple down? So this is what it means. Will it float? Okay, with the end horizontal. This is horizontal. Okay, will it rotate? Will it topple down? So this definitely the shape. The shape is this. The shape of I naught is circular. Okay, which is pi d the power of 4 over 64. So pi multiply with diameter 0.25, the power of 4 over 64, you will have 0.000192 meter power of 4. Okay, then substitute directly. I naught is 0.000192. Divide with the displaced volume is this one, 0.01 minus Cg, the distance C to G. Okay, how to calculate, how to get the Cg? Minus what? What minus what?
0.125 minus 0.102.
Yes, perfect. Zero point 023 meter. Okay. 0.023. So after you plug in the value, calculate everything, you get negative 0.004 meter. So it is unstable. You can also look at here. Can you see? It is in opposite direction or in the same facing to each other. It is unstable, right? Because it is pushing each other. Okay, definitely lah when you draw, okay, you assume it is unstable, you must prove lah. This is proof with the proof of calculation. Alright? Any questions so far?
No, Doctor.
Okay, thank you. Okay, next we learn about the linear accelerating container. Okay, so we take a break 5 minutes. Okay, you can review.
So, Doktor, kalau dia positif, that means stable. Macam tu. Saya terlawak masuk ni.
Okay, class. Shall we begin? Okay. Are you still
Yes.
all right?
Yeah.
Okay, now we proceed to the linear accelerating container. After this, we're gonna have the activity. All right. So, what is accelerating container in linearly? So, in this section of fluid will be at rest relative to the reference frame. That is linearly accelerating with horizontal component AX and vertical component AZ. So, the equation 236 simplify to. Okay, basically this is the hydrostatic equation. I believe you still remember the last class we derived the hydrostatic equation. Okay, do you still remember? What's our hydrostatic equation? Anyone? The one that you use for manometer measurement? Which is P2 minus P1 equal to negative gamma of fluid. Okay, or the rho G, okay, the rho of the fluid multiply with Z.
Z2 minus Z1.
Yes, perfect. This is our hydrostatic equation. Do you see any similarity in here? Is there any similarity? And what is the difference? Any similarity or any difference? Okay, what kind of similarity can you see?
Delta Z.
Okay, delta Z. Okay, good. And then? Okay, the change P2 minus P1 is what?
Delta P.
Delta P. So can you see? This delta P this is a delta P and this is delta Z. And you see this is negative and this is negative. And this is rho and this is rho. This gravity, what is gravity? Gravity, where can you see the similarity? The gravity is here, right? Gravity is what? Gravity is acceleration or only gravity? Or gravity is a gravitational acceleration? What do you think of gravity?
Gravitational acceleration.
Yes, gravity is gravitational acceleration. So, when we consider the container accelerating, that means it has external acceleration. So that means we have to plus AZ. Okay, instead of the free fall, this is the gravity, the free fall. We have the acceleration also in the Z direction. We have the acceleration in Y direction. And we have the acceleration in X direction. That means this is 3 component. This is only 1 component, which is in Z direction only. So, consider only 2 direction, which is X and Z. Thus, we can eliminate the Y direction. So, the equation now become this equation. Okay, so the change of pressure equal to negative rho AX dx. Negative rho G plus AZ dz. So this is the accelerating container. You can see see we have the container. This is container. Inside the container, we have the fluid. Why the fluid behave like this? This is because the container moving, okay, in the right direction with the acceleration ax and, okay, with the acceleration a. So this acceleration is, we can divide into ax and az. Alright. Do you think the water is static? The water inside this. Is it the water static? Not change?
No.
Okay, yes. Perfect. That was. The water is static. Because why? Because it refer to the reference frame. So now our reference frame become like this. This is our reference frame. The container now is become our reference. Okay. So let's say this point, when we refer to this location, even though it is keep moving, the distance here, when you try to, when you have, for example, you have the one object, floating object, you can measure the distance. Even it is moving, it is always the same. Okay, because the reference frame now here, this is a reference. Okay. Reference. Okay, reference. Even you have one object here, you try to measure from this distance. Even it is keep moving with acceleration, it always the same. Okay, now we refer the water in equilibrium state. So from this one, integrating between two arbitrary points, 1 and 2, result in P2 minus P1. Now it is the same. Okay, let me show you. Okay, I want to integrate this and integrate this. I will get between 2 points here. Okay, let's say point, this is point 1 and this is point 2. Alright. And here, okay, this is the coordinate lah. This is 0. This is x, this is z. Okay, definitely this is, okay, integrate this point, you will get P2 minus P1. Okay, you integrate this one, you will get negative rho AX x2 minus x1. You must make sure it is the same here, 2 with 2. And then this one, integrate z2 minus z1. So you will end up this equation. Since the point 1 and point 2 is exposed to the atmospheric pressure, it is on top of the surface. What do you think of pressure 1 and pressure 2? Is it the same?
Yes.
Oh, yes. So when it is the same, can we cancel? Yes, we can cancel out. This term becomes 0. And then we rearrange this equation. It will end up to be this equation. Okay. So now you must remember we have two equations, which is this one. Tangent alpha, what is z? Tangent alpha is equal to, okay, this is alpha. Okay, the tangent, if you want to get tangent alpha, it is opposite over adjacent. So opposite is this one. So how to calculate the distance here? Definitely Z1 minus Z2. Okay, adjacent is this one. definitely x2 minus x1. Okay, this is only distance here. Okay. Why it is x2 minus x1? Why at the denominator? Why at the numerator it is 1 minus 2? Okay. I want to show you why. Okay. In order to get distance, this distance, what should I subtract? Z1 minus Z2 or Z2 minus Z1? Which is higher, 1 or 2?
1.
1.
Yeah. Yes, 1 minus 2. How about this one? Which one is higher? 2 or 1? 1 or 2?
2.
2.
Yeah. Yes, 2 is higher. For example, we start here from 0, right? We start from 0. And this is got value. At the right is positive. This is negative. So definitely x2 minus x1. That is why you will have this equation. Okay. For this part, this is, okay, z1 minus z2 over x2 minus x1. Okay, another equation, tangent alpha, it is, this is basically the gravity acceleration, x first, g plus az. This is the, this is coming from this equation lah, from the top one. Okay, from this one. Okay, let's try example. The tank shown in figure below accelerated to the right. Calculate acceleration Ex needed to cause the free surface. So the question asks to calculate this one, Ex, in order to cause this happen. This one. Okay. That means the tip of this touching this A. Okay, from here, the tip of the water initially touching to this one. Also find pressure at B. So the question asks find the pressure at B. PB. PB. And the total force acting at the bottom of the tank is if the width is 1 meter. That means the width is 1 meter. Alright. So how to access this? How to solve this? The first we can write down our equation. Okay. This is formula tangent alpha equal to the change in the z direction over the change in x direction. Okay, tangent alpha also the acceleration in x direction over g plus a2. Az, sorry. Okay. So, the first step, I can see it gives me the clue. So, what's the clue? You can see the clue is x. Why I need to get the x? Anyone? Why I need to get the x?
Nak masuk dalam formula.
Okay, what's the relation of x to dengan alpha? What's the relation x to alpha?
Nak cari degree sudut.
Yes. So, remember our tangent. Alpha is opposite over adjacent. So, this is alpha. Definitely, we need to get the opposite. What do you think of the opposite? What's the value of opposite? What's the value of opposite?
1.2.
Yes, perfect. 1.2. You can see? Alright. What is the value of adjacent?
1. Right. 2.
What is the value of adjacent? Okay. The adjacent, this one. From here.
X.
X. You cannot simply divide by 2 tau. Okay. It is X. So, how to get X? Okay, we can use the volume after, volume before and volume after. Volume of air before equal to volume of air after. After. Okay. So before is this. Even it is move acceleration, the volume still the same. The volume here. Okay, what is the volume of before? Which is 0.2 multiply with 2 meter multiply with the width of the tank 1 meter. Equal to volume of after, which is triangle, right? Triangle shape, which is half multiply with x multiply with 1.2. Then you will get x to be 0.667 meter. Okay, so it is not 1. You can see even it is by our eyes, by our naked eyes, it seems like 1. But after we calculate, it is 0.667. Okay. Right. So next is we can get the tangent alpha, which is 1.2 divided with 0.667, which is 1.8. Okay, this is not alpha, yeah, tangent alpha. Okay, if you want to get alpha, you can inverse lah, tangent, shift tangent alpha. Okay, the question asks to get alpha to get the AX. So this is AX. Okay, AX we need to find. So correlate the tangent alpha equal AX G plus AZ. Okay, do you think we have the AZ? AZ, the Z component. Class, do you think we have the AZ? What kind of motion is this? Is it only horizontal motion or in the inclined motion?
Horizontal.
Horizontal only. When it is horizontal motion, do you think there is an acceleration in Z direction?
No, 0.
No, 0. So no motion, no acceleration in Z direction. Cancel. Thus, we can have Ax equal to G tangent alpha. So Ax is equal to 9.81. Tangent alpha 1.8. You will get 17.66 meter per second squared. Okay, simple. Find the PB. Okay, the pressure at B. Remember, we have this equation, right? Okay. We have the change of pressure. Okay, the change of pressure. P2 minus P1 equal to negative rho AX, X2 minus X1. Okay, since there is no motion in Z direction, we can cancel, we only use this equation only at two different points. Okay, so we can use the equation P2 minus P1 equal to negative rho. Okay, negative rho AX x2 minus x1. This is the general equation. However, we don't have specified yet 1 and 2. Why don't we use A and B? Okay, so let's say this is PA and this is PB. We can replace 1 with A and 2 with B. So PB minus PA equal to negative rho AX. This is XB minus XA. Okay, point A. Do you think we have the pressure at A? PA. What do you think the pressure at A?
Atmospheric pressure.
Atmospheric pressure. Yes, thank you. That was correct. Now, can you see? At point A, it is totally exposed to the air. Definitely, it is at atmospheric pressure. We consider as 0. We can cancel out. So, what we left here is PB. PB, what we need to find? AX, we already discovered. XB minus XA. Okay, how to get XB? Okay, when we refer to get XB, okay, we must specify. Okay, this is the coordinate lah. This is Z, this is X. Okay, now our reference point at B. So B is 0. So XB is 0. How to get XA? Is it 0?
2.
Yes, XA is 2. Why 2? Because from B to A is 2 meter. Right. So definitely B is 0, to the right is 2. So from here, XB is 0 and XA is 2. Right, substitute directly. Okay, density of the water is negative 1000. Okay, negative here, 1000. EX is here, 17.66. XB is 0 minus XA is 2. Then you will get positive number, 35.3 kilo Pascal. Okay, that is question to get the pressure at B. Alright, so the force acting on the bottom of the tank if the width is 1 meter. Okay, to calculate the force acting at the tank, for example, we have the force. Okay, at the bottom, we can see this is the shape. When we look at from here lah. Definitely, it will have the pressure. This is pressure at B. This is pressure at A. Pressure at A is 0 lah, basically. So, it is something like this. Okay. The pressure gradually decrease linearly, yeah, because of the depth. So from here, to find the total force acting on the bottom of the tank, we realize that the pressure distribution is decreasing linearly from PB to PA. Hence, we can use the average pressure over the bottom of the tank. Okay. So we can use the average pressure F to calculate the force. PB plus PA divided by 2 multiply with the area. Okay, PB is 35.3 plus 0. This is, don't forget, kilonewton. Plus 0 over 2 multiply with the area of the tank, which is 2. Okay, this is 2 meter by 1 meter. 35.3 kilo Newton. Okay, that's it. That is the final answer. Okay, any question so far? Okay, clear class?
Doktor.
Clear
Yes.
tu.
Dekat TV yang atas tu kenapa doktor tulis kilopascal? Bawah kilonewton.
Sorry, kilopascal. Thank you. Okay. Alright. So far clear, yeah? How to calculate? Okay. Let's proceed on the next part. I have to I have to rush a little bit because I'm worried about your test one until Bernoulli equation. Okay, this lecture note under week 6 I have uploaded in the e-learning. Please download and fill up together. Okay, in this part we're going to understand, we're going to cover description of fluid motion, and the rest will be the classification of fluid flow and Bernoulli equation. Your exam until this one. Test 1. So, description of fluid flow. Okay. Allow us to get a more detailed analysis of the flow. For example, we have the fluid flow. Okay. Can you see the fluid flow have different pattern, different velocity, different direction? So, how do you analyze the flow? You must be wondering, right, how to analyze this kind of different flow. So, we're going to introduce you with the description of fluid flow. For example, okay, we need to know how the velocity varies over the cross-sectional area of pipe. That means we have the pipe here, we have the flow. The velocity of the water basically varies here. It is not the same. Okay. So can you see the velocity changing with the y direction? Okay, different value of y, different magnitude of velocity. It keep changing. Another example is how does pressure varies along the surface of an airplane wing. Okay, for example, this is the aerofoil. Okay, this is aerofoil shape, and then we have the flow. Okay. This flow will have different pressure. So this point pressure will be different pressure at here. P2 will have different pressure. So how does pressure varies? Okay, we can see different point will have different pressure. So we need to have the relationship that apply at a one point. Okay, normally we going to use the differential analysis lah. So just remember description of fluid flow. We have two description, okay, Lagrangian description and Eulerian description. For example, we have the police monitoring one car. Okay, so this is the fluid particle selected, and then position, velocity would be the function of time. Okay, it is very easier. Just imagine like this. This is the road. We have the road. And then we have a police. This is police car. Maybe the blue color lah, the police car. Okay, this is the police car. Okay, siren. And then this police car monitor one car. Only one car monitor. Okay. So this police always chasing one car. Whatever direction, this police will always follow one car. It will monitor only one car. So at that time, it will monitor. So that means the fluid particle selected. Okay, that means this car is selected. The position, velocity will be the function of time. Okay, this is the parameter lah. Whatever parameter, maybe the velocity, the displacement, the position will be the function of time. So the police will monitor from time to time. What happened to the position? What happened to the velocity? What happened to the acceleration? Something else like that. Okay. How about Eulerian description? Okay, it is kind of different. It is, we have the road, and then we have the car. Okay, so that means we have one police only monitor the area, the region only. So this is the monitoring the region. Okay, that means the fluid particle, okay, think of the control volume. This is like a control volume. Or consider looking through the window and watching the fluid. Okay, that means you are looking at the window and watching at this control volume. Individual particle are not monitored. Okay, this case individual particle, okay, are not monitored. So care alone only monitor about velocity, acceleration, etc. of whatever fluid. Fluid particle is at a certain location. At a certain time. Okay. So you must know the difference here at certain location and time. So this refer to time and location. So the difference here is that if car A pass through this one, okay, this is car A, do you think the police will monitor A at this position? No, it will only monitor within the control volume. If another car B, going through here, okay, so the police will monitor this car B within the control volume. So what it will monitor? It will monitor the position and the time. Different time will have different velocity as well as it will have different position. Do you think you can see A and B different position? So it will only monitor within the area. Okay, class? Understand?
Yes, Doctor.
Okay, perfect. Okay, I think that's all lah. Because I want to have the activity. Okay, we're gonna have the class. We're gonna have the lecture on the Thursday because I want to finish until Bernoulli. Okay, we have the activity class. This is a revised activity. Please participate. Go to your e-learning now. Okay, go to your e-learning. You are section 15, right? 15, 16 and 18. Any of you from section 17? Any one of you? Okay. I will create the forum under week 5. Okay, revise of chapter. Chapter what, yeah? Wait, let me check. Revise of chapter submerged body. Buoyancy. Okay, revise of chapter buoyancy. Buoyancy and buoyancy, stability, and linearly accelerating container. Okay, please in your own words, okay, please all of you highlight what have you learned in the chapter of buoyancy, stability and linearly accelerating container, and please point out your view. What have you learned? Okay. What have you learned? What have you learned on chapter buoyancy, stability and linearly accelerating container? Okay, I have created the forum. Okay. Please at least 5 points. If you get more point, it will be much more better. Okay. Okay, go to 14 November under week 5 and post your review. What have you learned on chapter buoyancy, stability and linearly accelerating container? At least 5 points. Okay, more than that will be better. I can see your name here. Okay, I post as well in chat. Sorry. In section 16 forum. What have you learned? Okay, please give maybe 10 points. What have you learned? Okay, you can create. Okay. Alright. Forum. Please, I want to look at your understanding. What have you learned? What do you understand? You can share. Your friend also want to look at. Okay, please start from now. I will monitor. Okay, go to section 18. Okay, how to do that? What have you learned? Okay, add new discussion. Okay, your name. Okay, your name please. Maybe Daus. Daus Aiman. Daus apa? Daus Aiman, right? Aiman. Okay, just Daus Aiman. And then point 1, I learned about buoyancy formula. Okay, what's the formula? Okay, FB equal to rho rho G V. So you can say V is a displaced volume, something like that. So I learned how to differentiate the centroid with the center of gravity. Okay, class, do you understand?
Yes, Doctor.
Yes, Doctor.
Okay. Okay, please, I want to look at your understanding. Please cooperate. I want to look at your point of view, basically. What have you understand? What have you learned? Okay, Daus, you are section what? What's your section, Daus?
15.
15, yeah, okay. Section 15, okay. There are no discussion topic yet. Okay, please add. Look at section this one. Okay, nothing. Please do so. Nothing. Okay, I'm giving you 5 minutes lah to write down what. It is not necessarily accurate, alright? It is not necessarily right. Just, it is subjective, just your point of view. So I can correct you, okay? If you have any trouble, any issue. Okay, remember on Thursday we're gonna have the class as a lecture. Okay, class, are you able to add new discussion topic?
Yes.
Okay. Okay, I share again the fill up lecture note. Okay, maybe you can look at the WhatsApp group. Okay, I try to share for lecture note, and maybe you have some idea lah how to consider.
So do we like give formulas that we learned and explain the formulas? Or
Yes, okay, yes, good. If you explain the formula, you know very well how to apply the formula during the exam. It is not necessarily right. I want to know your thoughts, your point of view. Okay, I try to share. You can see the lecture note. Okay. Okay, I have shared in the WhatsApp. Maybe you have idea after look at the lecture note. And oh, we have one from section 15. Ang To Zuan. Okay, let's see. You learn about normally center of buoyancy force below the center of gravity. Not normally tau, not normally. Ang To Zuan, it depends on the submerged body. Okay, if it is fully submerged, maybe at the same position. If it is half of the submerged, half floating, half not, it will change. Okay, metacentric height. Okay, GM positive, correct. Unstable. Okay, tangent. Okay, good. Z2. Okay, Z1 minus Z2. Okay, this is maybe the change lah. The delta P.
sir, the PDF does not open.
The PDF cannot work. Let me check. Wait, yeah, it is still uploading. Wait for a while. Okay, now. Okay, it is invalid format. Alright, I think there is a problem. E3. Okay. Okay, I think I have problem lah. It's okay. Just put anything what you have learned. This is very good. Okay, we have Ong To Zuan. Okay. We have Firdaus Aiman. Okay, the stability of submerged body is based on direction of weight. Okay. Okay, good. This is depends on the positive and negative. Linearly accelerating container only contribute 2 point to component only, while the hydrostatic equation only one component in Y. Okay, this is involved in the X and Z direction. Fluid flow varies. Okay, this is how you want to have the flow description. Lagnarian, this is you have to check lah. Lagrangian, Eulerian. Lagrangian, what is what? Eulerian is what? Okay. You can imagine like a police lah following a car. Eulerian is like you yourself look at the view of the road and see what happened to the road A, to the car A, B and C. Okay, you can look at Siti Aisyah. Banyak ni. Saya tahu bezakan center gravity dengan centroid. Okay, perfect. Formula cari FB, lambda. Lambda? Lambda different lah. It's not lambda. It is gamma. Lambda like this. Okay, lambda is different. Let me show you. Lambda is different than gamma, ya. Siti Aisyah, this is lambda. Okay, gamma is this. You are using this one. This is physics ni. Okay, this is physics. You know the wave, right? The wave 1, wave 2, wave 3. This is lambda lah. Okay. But for gamma, it is specific weight. Okay, the Newton over meter cubic, which is the weight over volume. Okay. Saya tahu yang centroid depend on displaced volume. Okay, correct. Location CG partially okay. This is okay lah. Kalau GM positive, stable, negative, unstable. Okay, moment of inertia minus V over V minus CG. Okay. Kena cari minus CG. Formula seakan sama dengan hydrostatic equation. Cari angle guna TOA. Okay, yes. Good. Okay. Please, we take a look about section 16. Muhammad Shazman. Buoyancy force act on the central. Okay, perfect. Must remember, not as buoyancy force at C. FB gamma. Okay, good. Stability, center unstable, rotation will occur. Okay. Equation derived. Okay, perfect. Equation derived. Good. Hazim. I learned about stability can be calculated. Okay, good. Yes. Lagrangian description monitor selected particle. Good. At certain time. At the function of time. Okay. Eulerian description monitor the flow in the certain area, or the area is control volume. Okay. Centroid depend on the depth of container submerged. Okay, good. Okay, this is good. This is in the horizontal motion lah. When there is a pushing and pulling force, the center of gravity will unstable. Okay. This one, only pushing je. Pushing force, it is unstable. Pulling force, it is stable. Okay, let's see section 18. Okay, what happened? Section Daniel only. The difference between C and G. The difference, no, okay. Yes, okay, excellent. Gamma, okay, good. Okay, yes, hydrostatic equation. You can write lah. P2 minus P1. Okay, stable, unstable, metacentric. Okay, perfect. Okay, class, you can see how many of you have done. Okay, excellent. 15 section 15. Almost. Many of you done. Okay, good, excellent. Okay, nice. Okay, next. 16. Okay, we have only 6 student done. 18. Okay, only Daniel. Only Daniel. Okay. Okay, class, it's end time. Please, after this, at the end of the class, at 5 o'clock lah, I give you time. Please done this before 5 p.m. Please explain your point of view. What have you learned on chapter buoyancy, stability and accelerating container. Okay, before 5 o'clock, yeah? Alright, I think that's all for today's session. Okay, I think okay, I end my session with Assalamualaikum warahmatullahi wabarakatuh.
Salam doktor. Thank you doktor.
Doktor. Thank you, Doktor.
Thank you,
Okay,
Doctor.
welcome.
Oh,
Thank you, Doctor.
have a nice day doktor.
Okay, thank you.